In this module, we'll learn some basics about spectroscopy, and first we'll discuss what are the learning outcomes, then a brief introduction will be given. We'll talk about what a spectrum is, introduction to spectroscopy, and the important question, why study spectroscopy? Then we'll talk about intensities of transitions, and we'll see that they depend a lot on the Boltzmann distribution law, and we'll also discuss a new aspect, that is Einstein's coefficients. Talk about spectral line broadening, and then sign off with a brief summary. In this module, we will discuss the various ways light can interact with matter. After studying this module, you shall be able to grasp the important ideas of Bohr's theory of the structure of atomic hydrogen. But before discussing this, we will also review the experimental observations of the atomic spectrum of hydrogen. Then we first talk about the interaction of light with matter. When a beam of electromagnetic radiation strikes matter, changes are caused in both because of this interaction. We shall now see what happens to the matter when it is struck by electromagnetic radiation. Now first we will consider light as an electromagnetic wave. When it encounters an object, absorption can take place, matter takes energy from the light, or emission takes place in which the matter with which it is interacting releases the energy as light. Transmission can occur, that means matter allows light to pass through it. For example, if it is transparent like glass or water. Reflection, matter repels light in another direction. Refraction can take place, the light wave changes direction on entering one medium from another. Scattering may take place, that is matter bounces the wave in many directions. Or diffraction may take place, that is there is bending and spreading of waves through the aperture or around the edge of the matter. So all these things can occur if the light is considered as a wave. Now when does a spectrum result? In spectroscopy, we are interested in the absorption and emission of radiation by matter and its consequences. We are not interested in any one of the other phenomena. We are only interested in the absorption or emission of radiation by matter and what happens as a result. Now what is a spectrum? A spectrum is the distribution of photon energies coming from a light source. Now the important question is how many photons of each energy are emitted by the light source. Spectra are observed by passing light through a spectrograph. Now what does the spectrograph do? It breaks the light into its component wavelengths and spreads them apart, which is called dispersion. You know that Newton's experiment, even white light can be broken into 7 different colors because of different wavelengths. And what do we use to do that? We use either prisms or diffraction gratings. And we also know that the absorption and emission of photons is governed by the Bohr condition, that is that the energy absorbed is equal to the difference between two energy levels, that is delta E, and the frequency is related to it by the relation delta E is equal to h nu. This relation and the prism, which casts white light into its components with known wavelengths bent by known angles, gives us the tools we need to peer into the inner workings of atoms. Not only check their size, that is in atomic microscopy, we also determine experimentally their internal energy states. How do we know? When we light on a substance, we see what happens, what is the kind of light that comes out. The light that falls out is not smeared out over many wavelengths, but it is concentrated into several lines in atomic spectra. And this is what makes spectroscopy interesting, because if you measure the positions of these lines, you can find out what is the difference in the different energy levels. These lines mean incredibly precise energy differences between atomic states, since any energy the atom loses, the photon gains. You know there is conservation of energy, so if the atom loses any energy by emission of radiation, the photon, it gains this energy. Now modern atomic theory arose out of studies of the interaction of radiation with matter. Now why do we study spectroscopy? Besides atomic spectroscopy, there are various other kinds of spectroscopy, and each kind of spectroscopy tells us about the internal structure of atoms and molecules. Now, observation of molecular rotations is done in the microwave region, and it tells us about the structure of molecules, the bond distances, the bond angles, what we call the geometries. We also get to know their atomic masses. Molecular vibrations, these are seen in the infrared region. This is slightly higher than the microwave region, and it gives you information about the strengths of bonds, stretching and bending of bonds. Electronic transitions are observed in the ultraviolet and visible region, and they give information about electronic energy levels. So all these different kinds of spectroscopy, starting from atomic spectroscopy, gives you a lot of information about the atoms and molecules and their various energy levels, their geometries, their strength of bonds, and so on. Spectroscopy finds many uses, including determination of molecular structure, identification of unknown molecules, detection of known molecules. If you know that a molecule has a particular kind of spectrum, and you observe it somewhere where you can make out that this molecule is present in that particular atmosphere, and it also is used in measurement of concentration. If you know what molecule is there, the intensities of the lines tell us what is the concentration. So, coming to the intensities of transitions, they also depend upon various factors. When radiation falls on an atom or molecule, the oscillating electric field of the radiation, you know that the radiation has two fields, one is the electric field and one is the magnetic field, and we also said that the interaction with the magnetic field is negligible in comparison with the interaction with the electric field. So, it is the electric field's interaction that we are more concerned with. It interacts with the electrons, and in some cases it causes a transition from a lower energy state to a higher one. So, this results in absorption of radiation, or in case the transition is from a higher, it is already in a higher energy level, it can come down to a lower energy level by interaction with the electric field of the radiation, and then there is emission of radiation. The intensity of a transition from one quantum state to another, resulting from the interaction of electromagnetic radiation with a molecule, is dependent on matching the energy of the radiation with differences in the molecular energy levels. That is the Bohr's condition, that if you measure the frequency of the emitted radiation, then you know what is the difference in the two energy levels between which the transition took place. It is also dependent on the number of molecules populating the initial state of the transition. The intensity depends upon the obviously whether that transition takes place or not, but suppose there are more molecules in the lower energy state, then the intensity of the transition will be higher because there will be more molecules available to undergo the transition. So, population is a very important factor, and we know that population is governed by the Boltzmann distribution law. In general, the Boltzmann distribution tells us that the ratio of population varies exponentially with the energy difference. In fact, there is a negative exponential difference. That is the ratio of populations. Ni is the population of the ith energy level, that divided by Nj, the population of the jth energy level, is equal to the exponential of minus Ej minus Ei divided by the Boltzmann factor into T. Now, look at different kinds of energy modes. We said that there are electronic transitions, that means there are electronic energy levels. There are vibrational transitions, that means there are vibrational energy levels, and there are also different rotational energy levels. And we want to see at room temperature. Remember that this capital T is the temperature in Kelvin. So, when I say at room temperature and we take it as 25 degrees centigrade, you have to substitute 298.15 Kelvin for the temperature. Now, we calculate the population distribution for 1 mole. The denominator of the exponent, it will take the value. It is, you know that Kb is equal to R by Na. So, R is equal to Na by Kb, and this is equal to 8.314 joule per Kelvin per mole, and RT we know at room temperature will be 298.15 into 8.314, and this works out to 24789 joule per mole. And remember the units. If R is being expressed in joules and RT will also be in joules, so the energy difference should also be in joules, it should not be in kilojoules. And otherwise you can convert RT to kilojoules per mole, and it turns out to be 2.48 kilojoules per mole after rounding up the fraction. And then you can talk about Ni by Nj in terms of the energy levels expressed in per mole, and that is why here we have used capital EI and EJ, because now we are talking about per mole, and we have replaced the Boltzmann factor by the gas constant R. Now let us look at the electronic level populations. For an electronic level difference, delta E is quite high. The electronic levels are very there's a large difference in energies between different energy levels. So delta E is very high. If we take a hydrogen atom in the gas phase, we'll take this example, then delta E is approximately equal to 1000 kilojoules per mole. That means the difference, you know that the hydrogen atom in its ground state has one electron in the 1s orbital. When it gets excited to the 2s level, there is an excited level at the 2s. The population of the 2s state relative to the ground state is a very high negative power of 10. So that means that the number of hydrogen atoms in the 2s state is negligible. So we can say that there is no 2s hydrogen atoms around at room temperature. But you can always increase the population by increasing the, so remember that there is a negative exponent. So if you increase the temperature, the power of 10 becomes smaller, and at stellar populations in the stars, there is sizable population of the 2s energy level. So it depends on two things, the energy difference, and it also depends upon the temperature. At room temperature, the electronic energy levels, none but the lowest energy level is populated unless it is an unusually low energy excited state. Now look at another kind of spectroscopy, vibrational level, what are the populations? Now in the vibrational modes, we can take the example of carbon monoxide molecules. The vibrational quantum levels, the separation is around 25 kilojoules per mole. Compared to 1000 there, it is 25 kilojoules per mole, it is much smaller. The vibrational energy levels, the quantum number is given a symbol V, and this can have integer values 1, 2, 3. These are the higher energy levels, and these are much more closely spaced than the electronic energy levels. And here the difference in population is not that high, and that means if you have a system containing 20,000 molecules, then only about one molecule will be found in the excited states. And that means again we can say that very few molecules are present in the vibrational excited states. Coming to the rotational level populations, they are much more closely spaced. Remember that you observe rotational spectroscopy in the microwave region, so they are much more closely spaced. For carbon monoxide, the rotational energy levels are only 0.05 kilojoule per mole apart, and that means that about 3 molecules are present for every molecule present in the ground state. 3 molecules are present in the first excited state, which is very high compared to the previous cases. And now we've also multiplied by 3. Why did we multiply by 3? Because in rotational energy levels there is also a degeneracy factor. Each higher energy level will have a degeneracy of 2j plus 1. That means even if the population of the ground state and the excited state is the same, there are 3 such energy levels, so the excited state will have a population of 3, and that has to be taken into account. And that is why you have to multiply by the degeneracy factor, which is given a symbol G. And thus at room temperature, there are practically no molecules in the electronic excited states. This is what we saw. Very few molecules in excited vibrational states, and a large number of molecules in the excited rotational states. So this is an important finding. If the energy levels are close together, then you have many molecules in the upper excited states already present, and if the excited states are very high compared to the ground state, as in electronic spectroscopy, this doesn't happen, and all the molecules are in the ground state. So only absorption can take place, emission cannot take place. An important factor is the Einstein coefficients, which governs what kind of transitions take place, what their populations are, and so on. Suppose you have a system in thermal equilibrium. We were talking about systems at thermal equilibrium where none of the excited electronic states was there. The very few molecules were there in the vibrational excited state, and many of the ground state rotational energy levels were occupied. Now you bathe this system with electromagnetic radiation, and we talked about radiation density, which is given a symbol rho, and it is a function of the frequency. Now the transition from the ground state I to an excited state J occurs by absorption of radiation density, but this radiation density only of the precise frequency which corresponds to a difference in energy level, that is delta E is equal to h nu ij, will be absorbed, and this is required by Bohr's condition. The rate of induced transition is proportional to the population of the lower level and the radiation density at nu ij. Obviously, if there are more molecules in the ground state, there will be more transition, and that is why it depends upon the dN j by dt, the rate at which the population of the upper state is increasing will be given by the number of molecules in the ground state multiplied by the radiation density at the that particular frequency, multiplied by a factor which is Bij, and this is known as the Einstein coefficient of induced or stimulated absorption. It is a kind of probability, and it is called stimulated or induced because this is induced by radiation, and it gives us the probability of the transition. Similarly, there is a rate of induced emission, but obviously it depends upon the population of the upper state, or and in this case it is given by dnj by dt will be negative because the population is decreasing, and bji means from the population of j to I, nu ji into rho nu ij, and bji is now called the Einstein coefficient of induced emission. There it was absorption, now we are talking about emission, so it is the Einstein coefficient of induced emission. And as I said, the negative sign tells us that if this process occurs, the population of the upper state is decreasing. So this is the rate of decrease of population of the upper state. The figure tells you very clearly what happens. There is an arrow moving upwards that tells you that this is the probability of a transition from I to J. Then Bji is the transition probability from J to I, and there is another process that takes place, we will just talk about it. The system at higher energy state, you see a molecule which is in the ground state cannot spontaneously go to the upper state because you need energy to go to the upper state. So that can only be induced by radiation. But suppose it is in an upper state, it can always come down by losing energy spontaneously on its own without radiation being present. When we were talking about BJI, that was induced emission due to radiation. But there is, even if you switch off the light source, the upper level molecules will always come down to the ground state because of spontaneous emission. Spontaneously it loses an amount of energy, Ej minus Ei, that is the difference between the two energy levels, and comes back to the state I. This is governed by another Einstein coefficient, and this is called the Einstein coefficient of spontaneous emission, and this is not given a symbol B, it is given a symbol AJI from J to I, that is why we have used the symbol AJI. Now the number of molecules passing spontaneously from J to I is given by Nj into AJI. Remember, I have not put rho here because it does not depend upon the radiation density, because this is spontaneous. It is not being carried out by the radiation, it is happening on its own spontaneously. At equilibrium, the rate of upward transition must balance that of downward transition. What do we mean by equilibrium? There is no change in the population, and this means that the rate at which molecules are going up will be balanced by the rate at which the molecules are coming down, and so I can equate these two conditions by writing Ni Bij, the first condition, the spontaneous absorption, rho at nu Ij is equal to Nj Bj rho nu j, but the other process should also be taken into account. The spontaneous emission leads to another term, Nj plus Nj Aj I. Application of Planck's radiation law and the Boltzmann distribution law leads to the relations between the three Einstein coefficients. First is that Gi into Bij is equal to Gj into Bji, and Abi by Bji is equal to 8 pi h nu cube by c cube is equal to 8 pi h nu bar cube, because we know nu by c is equal to nu bar, the wave number. The two relations are very important because they tell us that if you know any one Einstein coefficient, you can find out the others, because if you know Bij, you can find out Bji from the first relation, and if you know Bji, you can find Aji from the second relation. The ratio of spontaneous and induced emission processes is negligible for small frequencies because the denominator is large. Because the denominator contains C, that means that the ratio is small when the frequencies are small, and spontaneous processes are of consequence only for the visible and ultraviolet region where electronic transitions take place. So, we will not be bothered so much about spontaneous emission when we are talking about rotational or vibrational spectroscopy, only when we are talking about electronic spectroscopy. The net absorption intensity depends on the difference of the two induced processes. That is, that you see only radiation is carrying out only the induced processes. So, the net absorption will depend upon the number of molecules which are going up minus the number of molecules which is going down, and this is given by Ni into Bij into rho nu ij minus Nj Bji into rho nu ij. And remember that nu ij is the same as nu ji, so I have simply written nu ij in both places, and this depends on the difference in the population of the two states. Suppose we assume for simplicity that Gi is equal to Ga, and in electronic transitions normally they are singly degenerate. We saw only in rotational spectroscopy that degeneracy is there. So, we will assume that Gi is equal to Gj, and that means that it just depends upon the difference in the two populations and the Einstein coefficients of induced absorption and induced emission. Now, we expect, that means strong lines for electronic and vibrational transitions because they have large energy gaps, and because the population difference is large in these cases, we saw that there are negligible number of molecules even for vibrational energy states in the upper states. So, there will be strong lines only for electronic and vibrational transitions because of because the net absorption of radiation is more in these two cases because the difference in populations is high. Now, we come to another aspect of spectroscopy, and this is line broadening. If you have run any spectrum, you will see that you normally do not get very sharp lines. Now, what are the reasons for line broadening, and where do you expect large amount of line broadening? This is what we will discuss in this section. Now, if the Bohr condition is satisfied, we would expect single line spectra, because only when the difference in energy levels is equal to h nu, then only that particular frequency will be absorbed. So, there is only one frequency at which this will occur. So, we should expect only line spectra, and we also want very sharp peaks, but we will see even electronic transitions in molecules are very broad, and this is because you saw that the electronic transitions require larger amount of energy. When you supply this much amount of energy, then that energy is enough to also cause rotational and vibrational transitions because they do not require so much energy. And you will find because of this that the electronic spectroscopy leads to very broad lines. Even atomic spectroscopy, because in an atom you can't have rotation or vibration. One atom can rotate, if it rotates it looks the same because it is spherical, and vibration you can only have when you have at least two atoms in a molecule. So, these are not possible in atomic spectra, and one would have expected very sharp lines, but even there they are not very sharp. Now, there are three main causes for line broadening. The first one is lifetime broadening, and the second is Doppler broadening. This is also pressure broadening. Which one prevails depends upon what kind of spectroscopy you are doing, what is the state of the matter that you are looking at, and so on. So, we will discuss each one in turn. We call lifetime broadening, it is actually a consequence of the Heisenberg uncertainty principle, and that is why it is a fundamental cause of broadening. And you cannot eliminate by any means, because this is a fundamental law, the Heisenberg uncertainty principle. Now, according to the Heisenberg uncertainty principle, and it governs energy and time, according to this principle, delta E into delta T, the uncertainty in the energy multiplied by the uncertainty in time, or the time taken for the transition, is given by the Heisenberg uncertainty principle in a similar fashion to the position and momentum uncertainty as h cross, and we will always denote by h cross h divided by 2 pi, h the Planck's constant divided by 2 pi. And if you substitute delta E is equal to h nu, the uncertainty in the frequency is equal to 1 by 2 pi tau, where tau is the lifetime of the upper state, and this is called the intrinsic or natural lifetime of the excited state. There is no uncertainty in the ground state energy, because left to itself the ground state will remain in that state forever. So, there the lifetime of the ground state is infinite, and that means that there is no uncertainty in the energy of the ground state. But the excited state has a finite lifetime tau, and since the mode of decay of the excited state after the radiation is switched off is spontaneous decay only. After you switch off the radiation, induced absorption or emission does not take place. So, tau is governed by the Einstein coefficient of spontaneous decay, and that means it is equal to 1 by Aij. It is like a rate constant Aij, and that is why if Aij is like a rate constant, it will have the dimensions of time inverse, second inverse, and lifetime will be in second or time, whatever units you are using for time. Now, if the excited state is long lived, the spectral line width will be large, because tau is large. That means that delta nu will be small. Usually excited electronic states have lifetimes typically in the range of 10 raised power of minus 9 to 10 raised power of minus 8 second. Normal lifetimes are 10 raised power of minus 9 by 10 raised power of minus 8. Next kind of broadening is Doppler broadening, and in Doppler broadening the change in frequency depending upon the distance between the detector and the molecule. You must have observed this phenomenon or studied about in physics, the Doppler effect, and you might have observed it. Suppose you are on a road and there is an ambulance. The moment the ambulance starts coming towards you, you feel as if the frequency of the siren has increased, and when it is moving away from you, the frequency is decreased. Now, this is very nicely shown in this figure, and the same kind of effect is observed in spectra, that molecules which are moving away from the detector will be at a different frequency as compared to those, will absorb at a different frequency as those which are moving towards the detector, and this will lead to line broadening. And finally, we also have another kind of broadening which is called collisional or pressure broadening, and this is observed in gases. Now, collisions between molecules cause the energies to vary slightly, causing line broadening. The shape of the absorption or emission curve is generally affected by this kind of line broadening. The lifetime broadening and collisional broadening are homogeneous, that is, all molecules are similarly affected, and this gives rise to a Lorentzian line shape, and generally given a mathematical form, capital F as a function of omega, while Doppler broadening is inhomogeneous, because in Doppler broadening different molecules are affected differently depending upon their position, and they give rise to a Gaussian line shape, and this is generally given by a mathematical function g, which is a function of omega, and these are shown in figure. Solution phase spectra are usually dominated by the Gaussian line shape, and this is what you see. The Lorentzian lines are very sharp and they are higher, whereas the Gaussian lines, they are broader at the peak, and this is the difference between them. You can recognize the kind of line broadening by looking at the line shape. So, in summary, we can say that in spectroscopy, we are interested in the absorption and emission of radiation by matter and what happens as a result. The absorption and emission of photons both are governed by the Bohr condition, that is delta E is equal to h nu. Three processes govern transitions, There can be induced absorption or induced emission, and there can also be spontaneous emission. The intensities of lines depend on the difference in populations between the initial and final states, and spectral lines are usually broad due to various factors like the finite lifetimes of the excited states, Doppler broadening, pressure broadening, and vibrational fine structure.